Okay, well, let me go ahead and introduce Bhushan. He's an associate professor at University of British Columbia. His primary interests are in process modeling and control, and especially with data-driven models of a variety of chemical and biological systems. And these are typically nonlinear, hybrid, and time-varying, and the measurements are often noisy and irregular. So we're going to get a tutorial today from Bhushan on Bayesian Bayesian state parameter estimation in stochastic nonlinear systems. So I'll go ahead and turn it over to Bhushan right now. And Bhushan, if you want to mention anything about your background, feel free to do so.
Thank you, John, for the introduction. I think that you've mentioned whatever needs to be told about me, so that's fine. Can you guys hear me well and see my slides and so on? Okay. So Jeff, I'm not sure if this is the right presentation for you, because I think in planning and scheduling you're probably interested in steady state models. I'm going to be talking about dynamic models. So this is the kind of techniques that I'm going to introduce today are probably a bit more complicated than what you would need to estimate parameters in steady state models. Anyways, so let's get back to my presentation. I'm going to be talking about state and parameter estimation in stochastic nonlinear systems. And some of you listening to me today probably know what state and parameter estimation are already. And some of you who know it really well are probably wondering what more is there to learn about state and parameter estimation, because these are topics or research areas that have been very active for about 50 or 60 years, since 1950s. And if you look at linear systems, linear stochastic systems with Gaussian noise, these problems have been solved satisfactorily. In fact, there are a variety of applications of state and parameter estimation in linear systems with Gaussian noise. And on the other hand, if you have a nonlinear system, then it's extremely difficult to find state and parameters, especially nonlinear stochastic systems. And the reason is that the optimal solution to these problems involves a complex high-dimensional integral, and approximating that integral is extremely difficult. Most of you are probably familiar with extended Kalman filters. Extended Kalman filters can be used for state estimation in nonlinear stochastic systems. And the way extended Kalman filter works is by approximating the nonlinearity in a system. If you approximate the nonlinearity using first-order Taylor series approximation, you can use an extended Kalman filter. But the problem is, the performance of an extended Kalman filter depends on the type of nonlinearity you have. And the type of nonlinearity is something for which you have absolutely no leverage. You're given a process, you have to build a state estimator, you have absolutely no leverage over the nonlinearity of the process. You have to take whatever nonlinearity you have, right? In other words, the performance of an extended Kalman filter ultimately depends on the type of nonlinearity you have, and there's nothing you can do to improve its performance. In the last 2 decades or so, there's been a lot of activity especially in statistics and in some engineering disciplines as well, in bringing new ideas for state and parameter estimation, where you don't have to make any approximations on the nonlinearity of the process, unlike extended Kalman filters, right? The performance of an extended Kalman filter, as I mentioned, is limited by the type of nonlinearity you have. But with these new statistical methods, which are called sequential Monte Carlo methods, you can get whatever performance you want as long as you're willing to pay the price in terms of computational complexity. If you increase your computational complexity, you can increase the accuracy of your state estimates and also parameter estimates, right? And therefore, stochastic, these sequential Monte Carlo methods have gained popularity in the last 2 decades or so. I'm going to be talking about the sequential Monte Carlo method for state and parameter estimation. I want to make one point clear here. Most chemical engineers are used to state estimation, or used to calling what I'm going to describe later in the next slide state estimation. But in statistics literature and in electrical engineers, they often call this filtering. I'm going to use these two terms interchangeably in the rest of my presentation. So when I say state estimation or when I say a filter, it means the same thing. Okay. So let's talk about what estimation is. There are many processes, engineering processes, that are stochastic. For us in chemical engineering, these processes could be distillation columns, reactors, heat exchangers, and a variety of other processes that are stochastic. We deal with these processes in a variety of contexts, and these processes are often stochastic. They have some inputs, they have some outputs. Because these processes are stochastic, even if you apply the same input but repeat the experiment, the next time the output you're going to get is going to be different. In other words, for the same input, because of the stochastic nature of this process, the input is likely to change every time you repeat your experiment, right? Now we want to be able to use these inputs and outputs and perform some Bayesian inference to estimate certain unknown quantities in the process. And a variety of these processes can often be represented using a set of differential equations or a set of partial differential equations, or a combination of both, or sometimes these equations may even include algebraic equations. And in most cases, you can discretize those equations and write them in the general nonlinear state space form that I'm showing you here, where x's represent the state, thetas are the parameters, u are the inputs, v represents the state noise. State noise is a way of introducing uncertainty, both parametric and structural uncertainty into your system. And then you also have outputs. They're represented by y. There is measurement noise or output noise, wt. There are two functions that define the state transition from xt to xt. There's one function that defines the state transition from xt to xt plus 1. It's ft. There is another function gt that defines the relation between the states and the outputs. The assumption we're going to make here is that the states are not variables that we can directly measure. These, in typical chemical processes, these could be a variety of different variables. For instance, I've worked in the past with the pulp and paper industry, where measuring brightness in some cases is very difficult. You can't measure the brightness directly, or if you have the instruments, those instruments are not very accurate, or they fail quite often. So you can treat the measurements as unknown states. Using other quantities, other measurements in the process, you can hopefully estimate these brightness measurements or brightness values. Okay, so that's one example. You can come up with a variety of examples where process variables are not directly measurable. If they're not directly measurable, you can express the dynamics of the process in this form. Now, what we would like to do is use these inputs, the information from inputs and outputs. These are the only two things that we know. We don't know the states. Typically, we also don't know the parameters. We don't know the state noise. We don't know the measurement noise. We only know the inputs and the outputs. We want to use those and predict properties or densities of the two unknown quantities here, the states and the parameters. And the way it is done in Bayesian estimation is by approximating the density function, the joint density function of states and parameters, given or conditioned upon the measurements and the inputs. You typically also have some information about a priori density of the states and the parameters. So you want to use that information along with the input and the output measurements and come up with an algorithm that allows you to figure out what the densities of the states and the parameters are. So this, in general, is the estimation problem. And we often separate the estimation problem into state estimation and parameter estimation. In state estimation, we are interested in finding the density function of xt given the measurements and the inputs and the parameters. Okay, in state estimation, you assume that you know the parameters. If you don't know the parameters, you cannot perform state estimation. And in parameter estimation, which I think is a much harder problem, you don't assume that you know the states, but you want to get the density function of the parameters given the inputs and the outputs. Note the subtle difference between state estimation and the parameter estimation. In state estimation, you assume that you know the parameters, you know the inputs, you know the outputs. Based on all that information, what's the best we can say about the states in terms of their density function, right? And in parameter estimation, we assume that we only know the inputs and the outputs. We don't know the states, but we want to be able to come up with the best inference on the parameters. We want to know what the best possible density function of the parameter vector is going to be. Now, if you don't know the parameters, obviously you cannot perform state estimation. In that case, you can do what is called simultaneous state and parameter estimation, where you estimate both the states and the parameters simultaneously given inputs and outputs. So I'm going to be talking about state estimation first, and then I will talk about parameter estimation in two different contexts. There are two different ways of performing parameter estimation. One that's extremely slow, but is great in terms of the properties of the estimates you get. The other, which is extremely fast, but you cannot guarantee certain asymptotic convergence properties. And then I'm going to follow that up with a few examples. Okay, so I think I don't have to probably. Sorry, is there a question?
Yeah, Bhushan, this is John. I just wanted to ask a quick question here. If you could go back to the last slide. And actually, I wanted to ask this maybe to get your thoughts and also Jeff's thoughts on this. You know, you're writing, let's say you have a first principles model, you're doing some blending application, for example, in gasoline blending. If you have state noise, you're essentially allowing, for example, the material or energy balances that you've written to no longer be, you know, you're essentially not invalidating them, but you're allowing them to not be solved, you know, the material or energy balances. Jeff, have you dealt with this? You know, what's the appropriate way to, when you include state noise versus when you don't want to? It just seems like it would destroy the predictive quality of your first principles model somewhat.
Yeah, I think, you know, if I don't, in the stuff that we do, we really don't do, explicitly states. There's either, we either have essentially measured variables or unmeasured variables. So an unmeasured variable can either be a parameter or a parameter or a state. But it seems to me that the state noise is really, these are essentially constraint or equation variability, because the measurement noise is something that's, you know, associated with the actual measurement. But the state noise, I've always been puzzled. The state noise is a little bit more abstract. But if I relate it to, you know, variables and constraints, then it seems to be more constraint uncertainty. Again, I don't know if that's correct. So to answer your point, we really don't include that because it can also be structural. You know, you can have the wrong equation, right?
Right. So, John, I want to go back to your example of mass balance, right? So obviously, we cannot be violating the physical laws by artificially introducing state noise, right? It makes no sense. But my argument would be these physical laws in practice are rarely accurate. It's very accurate. I mean, if you're writing a mass balance, for instance, it'll probably satisfy your equations will probably satisfy mass balance equations, but only approximately, because maybe there are some leaks that you can't account for in your mass balance equation. You know, there's certain things that no matter what you're doing, it's almost impossible in any case to come up with an exact mass balance equation that is going to be satisfied under all circumstances, right? And this state noise is something that describes this uncertainty in not being able to write these equations exactly. Now, you're right. If you're doing an experiment mass balance equation has to be satisfied. There's just no doubt about it, right? There's no argument over that. But if you're writing the same thing in a big industrial plant, then there are going to be things that you can account for when you write your mass balance equation. Maybe there is a small leak that you can account for, which means your mass balance is not going to be exactly satisfied. By exactly satisfied, I mean the left-hand side and the right-hand side of your mass balance equation must be correct up to the 10th decimal point, right, or maybe 20th decimal point. That is something that is very difficult to achieve in practice. And I think the way to introduce that uncertainty, one way to introduce that uncertainty is to add state noise. It's easy to argue that it's not going to be very representative of the type of uncertainties we're going to face and so on. All that apart, I mean, this is the way I look at it is state noise gives you one more tuning parameter in your model that allows you to describe the uncertainty in the structure. If you have parametric uncertainty, you can add noise to your parameters. Okay, I think it's probably much easier to understand parametric uncertainty. Parametric uncertainty can arise due to, say, some uncertainty in your diffusion coefficients or uncertainty in reaction constant, right? That is something that all of us can easily relate to, but it's much harder to relate to the state noise that I have here because it's a tool or it's a tuning parameter to capture uncertainty in the model structure itself.
Yeah. I like how you put that. And you and Jeff both put that, how it's some uncertainty in how you've written the model equations to describe the actual process. So that makes a lot of sense.
Okay. And the interesting thing is, if you don't have the state noise, a lot of the Bayesian expressions and so on that I'm going to show you later are going to be quite trivial.
Okay. Yeah. We had a question from Krishna. He asked, "Is the joint posterior considered to be Gaussian?"
No. Okay. So that's a very important. That's a very good question. Right at the beginning of my presentation, I mentioned that Kalman filter has been around for over 50 years now. It's shown to be optimal for linear systems with Gaussian noise, right? If you have nonlinear systems with non-Gaussian noise, then Kalman filter is not optimal. In this presentation and the formulation that I'm going to show in the next few slides, I'm not going to assume that the state noise or the measurement noise is Gaussian. That's not a required condition. I'm also not going to impose any functional structure on FT or GT. FT and GT could be any functions. They could be continuous functions, discontinuous functions. In fact, they could just be a set of statements that define how state xt goes to xt plus 1. And the states don't have to be continuous variables. They could be binary variables. I think this setup, the Bayesian setup that I'm going to describe today, is very general, and you can use non-Gaussian noise and all kinds of things. And that's why these methods are extremely powerful and have gained popularity, especially in a variety of engineering disciplines in the last decade and a half or so. So I guess the simple answer to this question is no, they don't have to be Gaussian, and that is the power of Bayesian methods. Okay, so are there any other questions?
No other questions. You can go on.
Okay, great. Okay, so I'm going to skip. I had this slide just to show you a chemical engineering example where state or parameter estimation is important. This is another example in aeronautics where if you want to track the position of an aircraft using the radar, what you do is you receive the reflected radio signals from the aircraft at the radar. Based on that, it has to estimate the velocity and the position of the aircraft. And this is a state estimation problem because you don't know the position of the aircraft, but you have some signals or measurements. You want to infer the states in terms of position and velocity of the aircraft. So that's an example of a state estimation problem. Okay. So here is how state estimation is done. Now, this is a very general description of how state estimation is done. In fact, you can show that Kalman filter is also, or Kalman filter can also be put in this framework. Okay, so a variety of algorithms that you might have come across can often be put in this framework. And the framework is as follows. So you assume that there is a prior density function on the state. So when you start your process, when you start your simulation of the nonlinear state space model that I showed you in the previous slide, you assume that you have a density function for the initial state x0. Okay. So this is something that you have to provide to the algorithm. And then you do what is called a prediction step, where the idea is to find the density function of x at the next time instant. So if you're at time 0, then you want to find what the density function of x is going to be at time 1 based on all the measurements you have up to time 0. Up to time 0, you only have one measurement, y0, right? So you want to use all the measurements up to time t minus 1 in general and make a prediction on what the state is going to be at time t. This prediction, I'm going to call it the density function of xt given y1 to t minus 1. It's a one-step ahead predictor. And it turns out that using very simple Bayesian algebra, you can show that this density function is an integral of two other density functions. P of xt given xt minus 1 is the state transition density function. It tells you how state xt minus 1 goes to xt. You can obtain this from the nonlinear state space equations. In the previous slide, it's based on the function ft. This density function also depends on the assumptions you make about state noise. The other density function here is P of xt minus 1 given y1 to t minus 1. That density function is the density function of xt minus 1 at the previous time instant. Okay, that's something that you assume that you know. And then you have to find this integral to get the prediction. Once you get the prediction, what you can do is update your prediction with the new measurement yt and change your density function to P of xt given y1 to t. Okay, now you have all the information you possibly can have in this density function. You have all the measurements up to time t. Now this density function depends on the density function of yt given xt, which depends on the measurement equation, and it also depends on the update equation xt given y1 to t minus 1, and then some complex integral in the denominator. If you guys have any questions about these equations, please feel free to stop me. Okay. Now, most Bayesian methods generally give you a density function for the state estimate, and people doing control or fault detection or diagnosis and other applications of state estimation, they don't need a density function. They often need what is called a point estimate of the density function. Particle filters, the sequential Monte Carlo methods that I'm going to talk about, they provide more information than what you probably need in many applications. They give you the entire density function of the states. So if you want to get a point estimate or a single value of the state that makes sense, what you can do is find the expected value of the density function. You already have a density function for the state. You want to find the expected value of the state by using an integral that I have shown here. I'm sure most of you know that expected values are basically integrals, right? So expected value of xt is integral of xt multiplied by the density function of xt. Now this density function is obtained from the update step, and then you have to perform this integral. Once you do this, at the next time step, you go back and repeat these steps again and again until you finish all the data you have. Okay. Now, in theory or in principle, this looks like a very neat algorithm. You start with an a priori density function, you find a predictive density function, and then you update that predictive density function with the new measurement, and then you get a point estimate of the state by finding its expected value, right? This seems like a very simple, neat algorithm, but the problem is the integrals that I have shown you here are extremely complex, and oftentimes getting analytical expressions for these density functions is very difficult. And even if you have analytical expressions, finding the integrals is extremely complex. It depends, the dimensionality of these integrals depends on the size of your state space model and a few other things, right? So finding these integrals is extremely complex. They're multidimensional, and the question is, how do we approximate them? Different methods, Kalman filter, extended Kalman filter, and different types of Bayesian methods, all of them use different types of approximations, and they derive their name based on the approximations they use. If you look at literature, especially new graduate students, or they generally get overwhelmed by the number of filters that are out there in the literature. There are probably hundreds or thousands of these filters. All of them make some sort of approximation of these integrals. Okay. For Kalman filters, if you have a linear system, if you assume that the f and g functions that I showed you in the state space model are linear, and if you assume that the noise is Gaussian, it turns out that these integrals can actually be analytically calculated, and that's why for Kalman filters you have analytical expressions for these density functions and everything else, right? So Kalman filter is very elegant in that sense. But if you have nonlinear systems, if your noise is non-Gaussian, then you cannot analytically evaluate those integrals. Okay, so all these nonlinear filters are generally suboptimal, but they're numerically tractable. Okay, now the next question is, how do we approximate these density functions? I mentioned that there are no analytical solutions, therefore you cannot find exact solutions to those integrals. That's impossible. That's ruled out. So the next question we can ask is there a way we can approximate these integrals? There are many ways. I'm going to talk about one particular approach to approximate these integrals. What I'm going to do in the next slide is give you a quick overview of how density functions in general are approximated, and then show you in the next slide how it's done in sequential Monte Carlo methods, or particle filters as they are called in the context of nonlinear state space models. Okay. So we want to approximate these density functions. Let's see how if we can do that with a simple density function. Let's take a Gaussian density function. I'm now referring to the top left square box. You can see a Gaussian density function there. Let's suppose that we want to approximate a Gaussian density function. We know in MATLAB we can use a function called rand_n to generate samples from any Gaussian density function of interest, right? So let's suppose we generate 1,000 samples from that Gaussian density function. We can plot a histogram of those samples, and that histogram looks very similar to the Gaussian density function from which we took those samples. Right? This is something that all of you know. You've probably even tried it in some instances. So this is very intuitive. What it means is, if you know how to sample from a density function, you can actually plot a histogram and approximate the density function. Now it turns out that the mathematical equivalent of this histogram is a sum of Dirac delta functions. This is shown in the left side bottom box. So the density function, the Gaussian density function, which I'm calling here p of x, can actually be written as the sum of Dirac delta functions centered at the samples. So I've taken 1,000 samples. I'm calling those samples xi's. The n, capital N, is the number of samples. In this example, there are 1,000. Now you can write the density function, the Gaussian density function, approximately as the sum of these Dirac delta functions centered at the samples. And it turns out that this type of approximation of a density function is only possible if samples can be drawn from the density function of interest p of x. So if you know how to take samples from the density function p of x, then great, you can make this approximation. And the reason we need this approximation is once you have this summation, density function as a sum of Dirac delta function, you can take this density function, plug it back in the integrals that I showed you earlier, and write the integral as a simple sum over the samples. You probably know that integral of any function multiplied by a Dirac delta function is equal to the value of that function at the center of the Dirac delta function. Okay, so this is a very simple formula that we can use to approximate the integrals. If only we can write the density functions as summations of Dirac delta functions. Okay. Now, it's possible to do this approximation as a sum of Dirac delta functions if you know how to sample from the density function p of x. I'm going to call this density function p of x target density function. It's the density function of interest. It's the density function I want to approximate. If it's Gaussian, we know how to go to MATLAB and generate samples, right? But if it's not Gaussian, if it's some complex density function that we don't know how to sample from, even if we can sample from it, the naive way of doing that is going to be extremely inefficient. You'll waste a lot of time computationally. It's going to be very expensive. Then what can we do? What are the alternatives? One alternative that has become very popular is to use what is called importance density function. Now I'm referring to the top right block. An importance density function is basically another density function, an arbitrary density function that from which we know how to take samples, how to generate samples. It could be a Gaussian density function, and often people choose a Gaussian density function for the importance density function. In the figure here, Qx is the Gaussian density function. Px is the complex density function that I'm interested in approximating. Okay, but I don't know how to take samples from that density function. Now, if I can choose this importance density function Qx such that it has larger support than the density function of interest p of x, then it turns out that we can actually modify the mathematical equivalent density function that I showed you here by simply adding weights to it as shown in the bottom right hand block. And the idea behind using these weights is as follows. These weights are proportional to the density function, the target density function p, and the importance density function q at the sample xi. Okay. Now let's consider a simple example. John, can you guys see my cursor if I move?
Yeah, we can see that.
Okay. So let's say I pick a sample that's over here. The density of the p of x is extremely small in this area. Okay, and therefore the numerator of the weight zero. Okay, so this ratio is going to be approximately 0. And when you do this summation here, what happens is you naturally throw away or reject samples that don't have enough weight in the target density function. Okay, and by going through this process, you will be able to approximate the density function of interest. This is called importance sampling. The downside of this approach, it's not actually a downside, but the requirement of this approach is that you need to have a functional form of the density function p of x in order to do this sampling. If you don't have a functional form of p of x, then you cannot find these weights, right? So you have to know what p of x is, and that's why you have to use some of the Bayesian formulae that I showed you in the previous slide to get a functional form of those density functions. Once you have the functional form, you can use an importance density function. Typically, in a lot of state estimation problems, the state transition function p of xt given xt minus 1 is chosen as the importance density function. But it's not a requirement, but that is the most often chosen importance density function. Okay. Now, if you can do this, then you have an approximation of any density function that you're interested in. And once you have this approximation, you can plug it back in the integral. All the integrals become simple summations, and therefore you can find various properties of the states or the parameters. But even when it comes to parameters, we're going to do something very similar. Okay. This approach by itself is not it is problem prone. Okay, so there are some problems related to what is called degeneracy in particles. When you're sampling these, you want to make sure that there's enough variety in these samples. Okay, so if I take the Gaussian example, if all my particles end up right at the mean, then I won't be able to describe the density function with sufficient accuracy, right? So you don't want particles collapsing to one small area. That's something that we want to avoid. It was shown that in sequential Monte Carlo methods, if you don't take proper precautions, that can happen. One approach to avoid that is to do what is called resampling. So the full or the complete sequential Monte Carlo algorithm or particle filters involves resampling. So you keep doing this approximation of density function at every time sample. You do it, you get the weights, you get the samples, and then you resample the samples. Okay, and then you go to the next step. Use the propagation density functions that I showed you earlier. Because of that, because you're doing this process sequentially, these are called sequential Monte Carlo methods.
So Bhushan, I just had a question about this. I've seen some people, what they do is, they eliminate points that have low probability, and so they're not necessarily taking a full resampling, but at steps they maybe introduce or eliminate a certain number of points from that. Would you recommend that, or would you recommend more of the, just continue until you need to do a full resampling? And just want to get your thoughts on that.
I think the rigorous way to do this is to do resampling. Okay, so here's a comment that I can offer. I think it's right. When you do rigorous resampling, I mean, there's so much literature on how these density functions converge and so on. Right? There's a lot of literature, and they generally tend to assume that the resampling is done randomly, not arbitrarily by chopping off particles with low density function, right? And I don't know that all the convergence results are, if we assume that they're true for the standard way of doing that, I don't know if they're true if you arbitrarily remove particles with low probability.
Okay, great. I just want to get your thoughts on that.
So because you see, the beauty of these algorithms is it's not just arbitrary or empirical or ad hoc. When you go through this process, there are very clear, strong theoretical results that show you that when you go through this process, as you keep increasing the number of particles, you get better and better approximations of the target density P of x, right? Now, I don't know if that's going to be true if you were to arbitrarily throw off some particles because they have low weight, right? So I don't know how that process is going to impact the convergence of these density functions, because if I can't show convergence of these density functions, then it's not of much use, because the reason and the power of these methods is that they converge, and you get very good approximations of these complex density functions, right? If I can't prove that property, then I'll be a little hesitant to use those methods.
Great. I think Fernando had a comment here.
Okay.
Fernando, did you want to make a comment? I know you just unmuted your microphone. Okay, we can't hear you, Fernando. So feel free to ask away if you can get connected again. Okay, go ahead, Bhushan.
Okay, good. So what I'm going to do now is, in the previous slide, I showed you a bigger picture idea of how sequential Monte Carlo methods work. But here is the actual algorithm. So what you do is, the notation here is slightly different from what I showed you in the previous slide. What I showed you in the previous slide is I did a little bit of hand waving. They're not very rigorous, but the algorithm that I have here is very rigorous. I don't want to explain all the technical details because there's not enough time. But what I would like to highlight are the 4 steps here. At time t minus 1, you have an approximation of the density function. I'm calling it pi here. It was p in the previous slides. You have an approximation of that, and you have some samples, xt minus 1I, that are generated from this density function, and you have associated weights 1 over n. Capital N denotes the total number of particles. And then you go through a step called mutation. This is somewhat similar to the prediction step. What you do here is you generate the samples at time t by going through the importance sampling exercise that I talked about in the previous slide, and then you correct these samples using weights, certain weights. Once you have these weights and the samples, what you do is you resample these samples. After you resample, you change the weight to 1 over n, and the resampled particles are denoted xti. These resampled particles with their weights represent the posterior density function of states, and then the final representation of the density function is in terms of the Dirac delta functions. Okay, so this is the standard approach for doing particle filters. I know there are probably quite a few students in the audience. This approach is something that they can program, but they'll also find programs online that can do this. Okay, so with that I'm done with my state estimation part. I think I've already taken 15 minutes. John, do you want me to go through parameter estimation quickly, or do you want me to take
why don't we go ahead and open up for questions at this point, and we'll just see how many questions there are. We might have time for just a few more slides before we have to conclude. So let me open up for just a couple questions. If you have any questions on the previous material that Bhushan just shared, or just questions on state and parameter estimation that you'd like to ask. We'll open up for discussion. If you want to make a comment, feel free to just put it in the chat window or unmute your microphone, and go ahead and ask away. So any questions from the audience?
John, I can't see the chat window, so I think you'll probably have to read the questions to me.
Sure. Okay. Great. It looks like Hadis has a question.
Okay.
Okay, I have a question. What's the drawbacks of this particle sampling method?
Okay. The biggest drawback is the computationally expensive. If you want to do something extremely fast, this is probably not the method that you would want. But in most chemical engineering processes, the type of processes that we deal with have time constants of 1 hour or a few minutes and so on, right? In those cases, it's very easy. In fact, I have a slide that was going to come in the parameter estimation part, where I talk about the complexity of these algorithms, right? They vary with the dimensionality of your states. They also vary with the number of particles. The larger the number of particles, the more complex the algorithm is going to be computationally, and therefore the longer it's going to take to run your state estimation algorithm. So I think that is the biggest stumbling block, I would say, in implementing these algorithms. But I'm not unduly concerned about that right now, given the power of computers we have. I mean, I can run these algorithms extremely fast on my laptop. I don't even need a big desktop computer or a server. So yeah, that's the downside. Computational complexity is the downside.
Okay, great. Any other questions? Well, what I'll do is also just let me just steal the screen from you quickly, Bhushan, and just show some of these really quick. So if you're interested in, Bhushan mentioned there's a lot of code and tutorials out there. I just did a quick search on the internet. There's particle filter tutorials that you can download, for example, from MATLAB Central. Here's another one. This looks like it's doing some sort of vision. But there's a whole there's a lot of example code out there that can run you through that as well. I imagine Bhushan has some as well if you'd like to
Yeah, I have some code as well. Yeah, I don't mind sharing if somebody's interested.
Okay, great. Okay, well, I've got you back on, Bhushan. Any other questions from the audience? It looks like Hadis wanted to say one thing more.
Can I have one more question?
Okay.
How many particles do we need for estimating pocket density function?
Okay, so that's a very good question, right? I mean, how do you tune the number of particles? If you look at the algorithm, particle filter algorithm, there are mainly two tuning parameters. One is the number of particles, and the other is the importance density function. How do you choose the importance density function? How do you choose the number of samples? Choosing the importance density function is choosing the optimal importance density function is not easy, but the most common practice is to choose the transition density function as the importance density function. Now, coming back to the number of particles, I would say the number of particles that you need to choose would depend on the signal-to-noise ratio. If the signal-to-noise ratio is small, you will probably need a lot more particles. If the signal-to-noise ratio is large, you can probably do away with fewer particles. Now, that does not answer your question exactly in the sense that I'm not describing to use 10 particles or 15 particles, right? Now, such an answer would be extremely difficult because it's going to depend on a variety of factors like the signal-to-noise ratio, as I mentioned. It may also depend on the type of nonlinearity you have and so on. But in a variety of examples that I myself had done, I generally use about 150 to 200 particles. That has worked for me, but as I said, that may not work if you have really high signal-to-noise ratio, or for certain types of nonlinearity, it may not work, right? So I think it's going to be example or problem-based, and you may have to go through a trial and error exercise before you determine how many particles are good for you. The other thing to remember is the error that you get in the state estimates is going to depend on the number of particles you choose, right? So if you are willing to accept a little larger error so that you can minimize the computational complexity, then you will be okay with fewer particles. But if you want extremely accurate state, but you don't mind spending effort in computational complexity, then you should increase your particle. So the short answer to your question is there's no prescribed way of finding the number of particles for any general state estimation problem. It has to be, at some level, it's going to be a trial and error exercise.
John, is there time for another question?
Yeah, sure.
Yeah. Hi, Bhushan. It's Jeff Kelly. This is more of a general question. We see, and this relates a little bit more to moving horizon estimation. And so from I'm going to say it, but from more of an industrial perspective, that we hear lots of issues with extended Kalman filter in terms of being able to do state estimation and also parameter estimation, especially as you put, when there's nonlinearities and there's the error distribution is non-Gaussian. Now the question that I have is that from a chemical engineering perspective, the other technique that we have is nonlinear dynamic data reconciliation, correct? And so, essentially all we do is we have some covariance estimate for the measurements, and we put that into an objective function, and we minimize the sum of squares of residuals, and then we can fit some states, anything that's unmeasured, and of course we can fit parameters. And then what we do is, if we're using more of the advanced data rec theory, then we can actually do another optimization more than just fitting the values. We can do another bunch of matrix manipulations, and we can fit the covariance matrices for all of the measurements and the unmeasured variables, essentially, basically the states and parameters. So in some ways, is that an effective method to get good parameter estimation, for example? You know what I'm saying?
Okay, so yeah, so I think if if I understand you correctly, so I think you're from Queens, right?
Well, I did a bachelor's at Queens, and I did a master's at McMaster.
Oh, okay.
Yeah.
Kim McCauley, she and her group, I think Tom Harris was also probably involved, and a few others there. They had done a lot of work on parameter estimation in general nonlinear state space models, where I think they use an approach that you have described. The idea is to solve this problem in 2 stages. In the first stage, you estimate your parameters or states, and then in the second stage, you estimate the noise covariances. Right? So yeah, I mean that's definitely one approach. The estimation approach that I have here is based on what is called expectation maximization, where you solve for both parameters and the covariance matrices in just one step. So this what I have is slightly different, but I think that's fine. I think that's
okay.
an acceptable approach. Yeah, but it's for parameter estimation, not. Well, you're probably also doing state estimation. You can do.
Yeah, simultaneously, and then of course, another big important thing, of course, is to know that. Can you find, or maybe you just adopt from the data rec theory to make sure that your parameters and your states are observable, and then of course anything that's any output that you have, in some cases you like to know if it's redundant. Can you get those kinds of metrics?
Okay.
Out as well.
Okay, so that's a very interesting question. I want to answer this and your previous question as well in kind of 2 stages. One criticism I have about these MHE methods and so on is that they are all optimization-based methods. The dimensionality of the optimization problem depends on the size of your problem, the prediction horizons, and so on. And they're not convex optimization problems, and therefore you can never guarantee how well your optimization is going to work, right? On the other hand, if you look at Bayesian methods, there's no optimization involved, right? So they're free of optimization, and I think that's a great advantage of Bayesian methods. So that's one point I want to make.
Yeah. Sorry. Yeah. I don't mean to interrupt you, but I'm just curious that. Well, technically speaking, Bayesian methods, you still require matrix inversion, and so when you do equality constrained data rec, you could also argue that there's no optimization, but you're still inverting a matrix. You see what I mean?
Not quite in the Bayesian methods. Yeah. Maybe we can take that offline. We can
go ahead. Sorry.
Yeah. Okay.
I'm just curious.
Okay, so the other important point that you raised is observability, right? Is there something that these Bayesian methods give us in terms of observability? I want to make 2 points here. One is that observability is a very well-defined quantity for all control engineers when it comes to deterministic systems, right? You know the inputs and the outputs. You should be able to find the states exactly. You should be able to recover the states, right? But when it comes to stochastic systems, the state definition does not extend to stochastic systems, right? Because there's no unique way, because it's a stochastic system, inherently there's no unique way of reconstructing the states. They are going to be different, right? Because the system is stochastic. There has been an attempt in the literature on defining stochastic observability and so on, but it's not as well known as the traditional observability that we are used to as control engineers, right? Now, coming back to the core of your question, which is can we get any information about observability? I don't think there's a lot of work done in this area regarding observability because it's not an issue, it's not a constraint for estimating states and so on. And I'll tell you why that is the case. You're only going through these density functions. All of them are okay. Even if you can't observe the state, you will be able to estimate these density functions. But what is going to happen is if you cannot observe a state, what it means is there's not enough information of that state in the output, and therefore the state estimate density function, P of xt, given all the information, will be more or less same as its prior. Okay, so if the prior of a state does not change after performing Bayesian filtering or state estimation, then you can, with some confidence, conclude that there's not enough information about the state in the measurements. And that's why the prior has not changed after filtering or state estimation. Does it make sense? Yeah.
Mm-hmm. Okay. Yeah. Thanks.
So I think that's the way to do it. But I don't think this has been formalized anywhere in the literature. And that is the reason. If you read it, the Bayesian literature, nobody ever talks about observability. It's not even an issue there. But for us in control engineering, it's a big deal. Right?
Yeah, and it becomes real quick, and it becomes even more of a big deal when you start wanting to estimate parameters for a larger flow sheet.
Yeah. So
and that's,
yeah. If you don't mind, I'm going to show you one quick example here. There's an example on parameter estimation. Let's see. Okay. So yeah. Okay. So this is what is called a JAX-STAT signal transduction pathway model. It has a variety of parameters in that, and we've used some of these Bayesian techniques to estimate the parameters. And it turns out that if you look at A1 and A4 here, these parameters, the density, their posterior density functions, are reasonably sharp. But if you look at A3, it's not that sharp. The dotted line represents the true value of the parameter. It's not that sharp, right? So what it tells us is that A3 is not identifiable from the information we have. The prior on A3 was a uniform distribution. After going through the identification exercise, the uniform distribution does not change much, and therefore it looks like it's not identifiable.
Okay. Well, we have two quick questions here, and then we'll go ahead and conclude. We're about out of time. But Mansour had a question: if the noise is Gaussian, what is the advantage of particle filter in comparison with ensemble Kalman filter? And I think you had mentioned that before. You don't necessarily assume Gaussian, but if the noise is Gaussian, what is the advantage of particle filter?
Okay, so I mean, I think these are all approximations, different approximations. I would say particle filters are probably have the most watertight theoretical proofs on convergence and so on. Uncentered Kalman filters, for instance, assume that the noise is Gaussian. One thing you should remember is even if the noise is Gaussian, it does not necessarily mean the states are going to be Gaussian. Okay, noise could be Gaussian, but the states could be non-Gaussian, right? So if your states are non-Gaussian, then using some of those other methods may not be that efficient. But from my perspective, I mean, I think you have to kind of do this case by case. I've had examples where particle filters were extremely slow, but ensemble Kalman filters were much faster because of the way the algorithm is, and therefore I used ensemble Kalman filters. Right. So it depends on your application. How much computational complexity you're willing to incur, and it also depends on the accuracy you want. All these methods have different approximations. The advantage with particle filters, as I said, is you can get as good an approximation as you want by simply increasing the number of particles. I'm not sure if that's true with other types of filters.
Okay, great. And then Krishna had one question. There are several importance functions proposals. Would you like to recommend UKF or EKF posterior as an important function?
I don't have a good answer for that. I mean, would I recommend that? You see, one thing that I find counterintuitive is I think people do this in MHE, moving horizon estimation as well, for getting the arrival cost. They run another filter. Okay, so in MHE, for instance, people run EKF or UKF or ensemble Kalman filter to get the arrival cost and then implement MHE. In some sense, it kind of defeats the purpose because you're trying to estimate the states, but then you're saying, okay, I have another filter that I'm going to run in order to estimate these states, right? So you probably, in most cases, you probably don't have to run another ensemble Kalman filter or uncentered Kalman filter to get your particle filters going. You know, I would say in most cases, transition probability density function is good enough, unless you have some weird things going on in your process. So.
Okay, great. Any last burning questions from anyone? Okay, well, let me go ahead and conclude, and let's just thank you know, Bhushan for his presentation. I'll just mention we do have some additional presentations coming up next week. We have leapfrog applications in APC and plant optimization from Professor Reinhardt at Oklahoma State University. And then the following week, we have Michael Baldea at the University of Texas at Austin talking about performance of microchannel reactors, and then on down. So I'd say this as well. For those of you who would like to present some of your work, feel free to send me a title and your name, and we'll see if we can get you in on the schedule as well. But thanks, Bhushan, for presenting today. I thought that was a very interesting and informative tutorial on some of these state and parameter. Well, we didn't get really to the parameter estimation piece very much, but the state estimation was very informative and very good. So thank you so much for presenting today.
Thank you, guys.
Sorry.
Yeah. Did you have one more question?
Actually, the connection didn't work at the beginning, so I missed quite a bit of talk. Is it possible to have the slides, or to see the slides on some presentation like this, or the recording of it?
Yeah, you know, we also, let me go here, we have all of the presentations that are posted onto the YouTube channel. And so I'll post this later today. If you'd like to go back and review the slides or the presentation. And I'll leave that up to Bhushan if he wants to, if you want to get in contact with him, if he'd be willing to send out his slides.
Yeah, I don't mind sending slides.
Okay, so go ahead and get a hold of Bhushan if you'd like a copy of the slides. I'll post it here to the YouTube channel, and you can access that if you just go to the APMonitor.com website, and then click on the webinars, and then you can get to the YouTube channel right here.
Perfect. Thanks.
Okay, great. Thanks, dear. Okay, well, great, everyone. Thanks for joining, and thanks for Bhushan for presenting today.
Yeah, thank you, guys.
Thank you.